I want to welcome all of you. Welcome all of you to today's lecture once again. And the lecture for today is going to do the modeling of both the envelopment model and then the multiplier model. I just want to show you something as a reminder. We've done what you see on the screen. This is the envelopment model for output oriented. What shows that is an output oriented? Because in the constraint, you see the phi in blue attached to the output in the constraint. That is what will give you the clue that is an output oriented model. For envelopment, we also maximize the phi. Okay. And remember, this phi is 1 and above. How is that different from the input oriented? Well, this is the input oriented. In the input oriented, the theta is multiplying the input and not the output. And in order to distinguish between the input oriented score and the output oriented score, we use the theta for the input oriented score. And we use the phi for the output oriented score. Now, this score, when it is a star, it means it's a numerical value. All right. We've interpreted all of this the last time. What we are going to do today is very, very critical. What we are going to do is to eat up the relationship between the multiplier model and the envelopment model. Now, what is the main difference? We've said it before. The multiplier model, the way it works is different from the envelopment model. Okay. So the multiplier model, efficiency is defined using a ratio of the total output to the total input. That is when you're dealing with output orientation. Or a ratio of the total input over the total output, which is when you're dealing with it. The key point is that it's dealing with ratios. That's a multiplier model. And where is it important? Well, it is crucial when you want to look at areas of good and poor performance. Now, the envelopment model, which is commonly used in the literature, I also said that the multiplier model is for weight restrictions and trade-offs. The envelopment model, you define that using the boundary of the production possibilities of efficiency. So that one, you must have a convex envelopment, and that you measure everybody relative to the boundary of the technology set. It's useful when you want to identify the targets and the peers, and we shall do that today. The targets and the peers. So what I'm going to do is to take a very simple data set, hypothetical data set. We've used this before. That was the one we dealt with earlier. We are going to formulate the multiplier model for this. Okay, we're going to formulate the multiplier model using this data set. Now, let me just remind you of this multiplier model. Okay. It is ratio of the weighted sum of the output divided by the weighted sum of the input. Now, we are going to do for output orientation. Okay, we're going to do for output orientation. So it's going to be output over input, subject to the fact that if the same weights are assigned to every other firm in the industry, none of the firm will experience a user-specific upper bound of 1. Okay, so we know this already. How do we formulate this? Now, the first thing you have to do, and we are doing it for DMU1 here, and the input of DMU1 is 1. The output is also 1. Okay. So we are using the input of 1 and then the output of 1. So we got to maximize that ratio, the ratio of 1 over 1. But remember, each ratio must be weighted. Each value must be weighted. So the weight assigned to the output is usually U, and the weight assigned to the input is also V. But because there is only one output and one input, you have U1 and then V1. So if you are defining the efficiency, I'm going to write it here. Okay, keep this in mind. if you are defining the efficiency, you say that the efficiency of firm, efficiency score of DMU1. Okay. And this efficiency score we are going to have it in such a way that we are going to derive the V1, which is the input weight, and then the U1, which is the output weight. Now there's only one input and one output. So that's, if there were multiple, you have V1, V2, V3, depending on the number. So this efficiency score is going to be equal to the weighted output. Okay, the weighted output. And you can remember that the output has a value of 1. That output, that weighted output, it has a value of 1, 1. Let me see if I can show you that. So because it's going to have a value of 1, 1, there you go. Okay, so you're going to use this output 1U1 divided by 1V1. That's how it's going to be. Okay. So this is going to be 1U1 divided by 1V1. This is the efficiency, but this is subject to certain constraints. And what it is said is that the constraints are for every other firm. So if the same weight of U1 and V1 are applied to every other firm's inputs and outputs, they must not be more than a user-specific value of 1. So this is for all the others. So all the others must start with DMU1, its input and output, DMU2, its input and output. Okay. So the DMU1's input and output, you know that already, is 1U1 over 1V1. Okay. And this should be less than or equal to 1. Okay. Now you have to do the same thing for the other inputs and outputs. The second one, which is for DMU2, is 2 for the input and then 3 for the output. Remember, it is the output over the input, okay, in an output-oriented model. Okay, so let's do that. Let's write that for the second firm. And the output for DMU2 was 3 and 2, don't forget. So you're going to write this as 3U1 over 2V1 should be less or equal to 1. And then you go to the third DMU. Okay. The third DMU, what was the value of the third? Oops. What was the value of the third DMU? Let me go and check. I also want you to check. So this type, normally you have to have them in your mind. The third DMU is 2 and 4. So it's going to be 2 over 4, each one having the output. You will have to formulate this when you're doing on your own. Okay. So it's 2U1 over 4V1. And that should be less or equal to 1. And then you go to the next firm, and that is 5 and 5. And then you have 4 and 6. Okay. So let's do the 5 and 5. 5 and 5 is 5U1 over 5V1, less or equal to 1. The next one is 4 and 6. So 4U1 divided by 6V1, less or equal to 1. And then the last one, oh, I think these are 6 DMUs. Eh? They're not 5 DMUs, they are 6 DMUs. So the last one is 6 and 7. 6 for the output, 7 for the input. Okay. So you have 6, 7, 6 is U1, 7 is V1, less or equal to 1. So you've done this for each one of them, and you're making sure that the weight, the maximum weight is 1. And you have to add your non-negativity constraint, which is the fact that the U1 and then the V1 should be greater or equal to 0. Okay. The U1 and then the V1 should be greater or equal to 0. This is the fractional programming problem. Let me just show you how, and you got to learn this. So whatever sample model you have to formulate this fractional programming problem, which is a multiplier. Let me show you exactly how it becomes. So this is what you see on your screen there. This is what you have as a model. And one thing that is interesting is that I think I missed something slightly, but it doesn't matter. What matters is that you know what you're doing. If you look at the last constraint is supposed to be less than or equal to 1. Okay. I've effected that change. But it's supposed to be less than or equal to 1. Okay. Less than or equal to 1. So that is how the formulation is. But this is a fractional programming problem. You got to linearize it. Okay? So how do you linearize it? Linearizing means that you are simply trying to convert it into a linear form. Now, there's a very simple way you can convert this. One of them is cross multiply. But in the process of linearizing, you have to understand the orientation you are dealing with, as well as, okay, somebody says V2 should be V1. Okay, yeah, that's true. For some of them, I had V1. V1 is supposed to be V2. Let me just make sure that you have that correctly there. I'm coming. I want to be sure. I want to be sure that you have exactly what I'm looking for. So the V2 is off. You can identify that here, and you'll notice that this is where the V2 was having a bit of a challenge. Okay. So the best way to linearize this is cross multiply, but you have to understand the principle of linearization. You set the one that you are dealing with, you set it to equal to 1. Okay. So this is an output orientation. Okay. Is it? Yeah, this is an output orientation. So because it's an output orientation, you got it. The fractional programming model has to be linearized by setting the denominator in the ratio to 1. Now, when you look at this, the denominator in the original efficiency is 1v1. So that will be one of the constraints which will be set to 1. And then the numerator, okay, the numerator will be maximized. Okay. So the numerator will be maximized. Okay. So how do you do that? Well, if you are maximizing the numerator, let's use any letter to represent the numerator. So here we are going to call it like F. Okay, let me just use something. So we're going to call it like F. Okay, and this F star is going to be maximizing the numerator, and the numerator is 1u1. Okay, after maximizing the numerator, the denominator in that fraction must be set to 1. Okay, so the denominator is 1v1, and this must be set equal to 1. And then the rest, you can just cross multiply. Okay, so you cross multiply this and that, and then move everything to the left-hand side so that the right-hand side will have 0. Okay. But in the process of doing that, you will also you will also change this inequality sign. Okay. So for the first DMU, when you cross multiply, it's going to be 1 B1, okay, less than or equal to 1. So it will be 1 U1 less than or equal to 1 V1. Okay. And when you move this one to this side, okay, it's like multiplying through by negative 1 V1. So that would mean that you're going to have 1 U1 minus 1 V1, okay, less than or equal to, but because you have applied a negative, get greater than or equal to 0. Okay. That is how you linearize, and you're going to use the same approach to linearize all of the other ones as well, so that the right-hand side becomes like 0. Okay. Everything follows that same principle. And the non-negativity constraint must still remain. The weight must still be positive, 0 or positive in that regard. So that is how you do that. That's how you convert the fractional programming problem to a linear programming model. Okay. And I think I made a slight mistake here. I'm supposed to have all of the sign. Okay. So here, there's no mistake there. If you look into the formulated model, okay, just watch it. I just want to show you. If you look into the formulated model, you set the denominator to 1, you maximize the numerator. Okay, you maximize the numerator. And then each of the constraints, you cross multiply. So this is a cross multiplication that I did. But when you move this one to this side, then the inequality sign will change. So that is how so this is the multiplier model, but it's a linearized form now. It's no longer a fractional programming problem. It's a linearized programming problem. All right. Now, the next thing is to write the envelopment version of this multiplier. And like I said, in any linear programming problem, we have a primal and we have a dual. We have a primal, we have a dual. We have a primal, we have a dual. Okay, so this is the dual and we are going to get a primal. How do you do that? The way you define it is important. Okay, so what is interesting with this one is that, and I'm going to show you something, because you have to get a trick of how you do the formulation, even if you have not done linear programming before. All of the items for this are the output. So you see that the outputs are on this side. If we had moved this one to the left-hand side, they would have been the inputs. The inputs are here. So we are going to create a constraint for the inputs and a constraint for the outputs. If the inputs are many, you create many of each one of them, you create a constraint for it. And what is going to happen is that because this is a maximization in the multiplier model, when we go into the envelopment model, it will become a minimization. Now, what are we minimizing? Well, in an input-oriented version, told you that, let me just use this one. In an input-oriented version, we use theta to represent the efficiency. In an output-oriented version, we use phi to represent the efficiency. So what we are doing is that we are minimizing, okay, the input, because this is an input-oriented model. Okay. Is it? Yes, there's an input, and we are going to do an input-oriented model. So we minimize the input. Okay, we could choose for the output, but we're going to do for the input. We minimize the input. And if you could remember the way the graph looks like, let me just remind you briefly how the graph looks like. If you have something like that, and you are drawing your graphs, if you are drawing your graph, you draw this first one, okay. You draw the second one, okay. You draw, say, the third one. This is your production possibility set, okay, the convex isopoint. And if you have an observation that is inside the frontier, say that you have another observation there, another observation there, somewhere on the frontier, somewhere on the frontier, somewhere on the frontier. Okay. What you do normally is that you try to, and this observation may be something like, let's say 6 and 4. Okay. So these are like the coordinates of the observation, say A. So if you want to estimate the efficiency score, what you do is that you draw a line, okay, from the origin to hit that particular frame. But in the process, it will cut through the convex isopoint. Okay, and we define efficiency, if you can remember. I'm just recapitulating. Okay, we define efficiency as the distance to the frontier divided by the distance to the fan, to the DM. That's what we said. So the distance to the frontier hits the section somewhere here. This is where it hits. And the distance to the fan goes further. And so the efficiency is going to be inefficient for that firm A, which is there. But how do we now move that firm A to the frontier? Okay. How do we now move that firm A? Let me just go back. How do you move, okay, to hit the frontier? Something must happen, because the coordinates there are 6 and 4. How do we reduce that 6 and that 4? Okay. Remember that this is an input-oriented model. And if it's an input-oriented model, what that means is that you're going to have something like x2 there and then x1 here. How do we now reduce the content of 6 and 4? You need something called theta. And so what the theta is doing is that the theta is multiplied. So this theta multiplies the 6, okay, and brings it down. And then the theta multiplies the 4 and brings it down along this until they hit the frontier. And this becomes the target or the benchmark. We'll come back to that. Okay. Now, what is interesting is that when you are formulating, what the theta is doing is, so the essence of the theta is that because this is an input orientation, the essence of the minimization, the essence of the optimization is to minimize. Minimize what? Minimize theta. But you see, in the process of minimizing theta, theta itself is multiplying some two things or some things. And so it will reduce the content of that thing is multiplying with. So the essence of the minimization here is that you are minimizing theta along the radial line until it hits. So that thing that will help us to minimize the 6 and 4 input towards the optimum level is that theta. And so with that understanding, you need to learn how to formulate the linear program. So you're going to, and since we are still doing it for DMU1, DMU1 will have an input called what? 1. Okay. So if you are going to, so let me just rewrite this here so that it becomes interesting to you. All right. So the efficiency, okay, the theta star, which is the efficiency score of DMU1, okay, or A. The theta star is going to be the efficiency score of DMU. This will be equal to minimizing that theta for that particular DMU, okay, with the intention, because it's a minimization, you have the intention of finding something. The intention is to find lambda and of course the theta square. The theta is objective function. The lambda you're going to learn are the intensity factors or the weights. And so in the process of minimizing this theta, and remember this theta is multiplying some other elements, which I've just shown in the graph. You minimize this subject to the constraint. So now you bring your optimization constraint. Subject to the constraint that the weighted sum of the inputs, okay? So this input, the weighted sum, of course, is going to change. The V's are going to change to a different value. The weighted sum of the input is less than the input of the firm you are assessing. And then the weighted sum of the output is greater than the output of the firm you are assessing. So what is the weighted sum? So you got to use something to represent that. So for the input, so you have to write an input constraint, as many of the input constraints as they are. Okay. Remember the generalized formulation. So what is the first input? The first input is 1. And that's for the firm, DMU1. So we weight it. And here we are using a different kind of weight parameter called lambda for the first firm. So we use lambda 1. It is a sum, so we'll bring a plus. Then you take the second input, and that is 2. You weight that with the firm, and that firm is firm 2. Then you add the third input, and that third input is 4. You weight that, and I'm picking it along this vertical line, okay? And then you take the fourth input, which is 5, you weight it, that is lambda 4, okay? Plus then the next input, which is 6, okay, which will be lambda 5. And then the last one is input 7, which is lambda 5, lambda 6. Okay. Now, all of this must be less than or equal to that very firm's input you are trying to minimize. And in this case, that firm is DME1. So it should be less than or equal to input 1. Okay. The rule is saying that it should not be more than the input of the DMU that you are actually measuring its efficiency. But of course, that is the input you are reducing. Remember, this is a linear program and you're going to run it one at a time for each firm. So we are doing it for firm 1. And so firm 1, because it's the one whose input you are minimizing, the theta must be given to that. So we attach the theta to that very input because we are doing input minimization here. Okay. So how does that look like? Let me just show you how this will look like practically. Okay. So this is how it looks like. This is for the start, the input. You do that for the input, but you do the same thing for the output. But for the output, you don't attach the theta to it. And like I said the last time, you're not attaching the theta to the output. Why are you not doing that? You are not attaching the theta to the output. You're attaching it only to the input above, not the output. Okay. Why? So you attach it to this input. You are not attaching it to the output because we are minimizing the input, holding the output constant. Okay. And so even though we are going to weight the sum of the output, okay, we are generating a weighted sum of the output, which is the sales here. And again, we are using the same lambda weight. So for the same DMU1, its weight is lambda 1. We are assigning the same weight to the input and to the output. So you do that, but you can see that we are not attaching the theta to the 1 for the output. And also you will notice that this is the weighted sum of the output of all the firms, including even the firm whose efficiency you are assessing. And this should be greater than or equal to 1. Now, if it is greater than 1, okay, now let's start with if it is equal to 1. What does that mean? It means that all the left-hand side are equal to the right-hand side. And so that will mean that that particular firm is efficient, okay, in that connection. But if it is greater than 1, okay, what it means is that that firm is inefficient. because it's not been able to utilize it. Now, if you look at the input orientation, the input side, okay, let me just go here. Look at the input side here. What it says is that the weighted sum of the input of all the firms, including even the DME1, okay, that was part of it. Okay. All the firms, this weighted sum should be less than the input of the DMU and the evaluation here. And that input of the evaluation is DME1. So the weight should be less than or equal to, if it is equal to, remember the left-hand side here, the two left-hand side here, they make up the technology set. Okay, so if this left-hand side is equal to the value, it means that that value is on the frontier. That is it. It means that it's on the frontier if it is equal to. But if it is less than, it means that it is somewhere interior or inside a frontier, and hence that particular firm is inefficient. What about the last constraint here? This last constraint here simply is a non-negativity constraint in linear programming, which says that the weight attached to the individual firm's input and output, the weights are supposed to be 0 or positive. 0 or positive. Now you might be wondering, what then is the weight? What then is the weight? Okay, I'll talk about them as we move on, but keep that in mind. Okay. So this is how you convert the original multiplier model to the now envelopment model. Okay. Any question? If you have a question, just raise your hand and then let me address it. Now let's go to the next one. You will do this in your thesis. You will formulate the model for the hypothetical firm. So it's important you learn how to do the fractional programming problem, linear programming multiplier problem, linear programming envelopment model. Oh, the theta being free, okay, allows the theta to take any particular value. It is used to determine the returns to scale at the firm level. I'll talk about this when we get to the VRS model. Okay, so you can see that the V1, okay, and the U1 that we had, okay, they are the input and the output weight. And they are now being represented by this formulation, the first and the second formulation, the staff formulation, the sales formulation. The sales formulation is all for the output, which in the multiplier it was U1. But here they are all being given lambda because the weight is assigned to the firm and not just to the variables, not just to the input and output, but assigned to the firm here. And that is why they will have the same weight. All right. So can I give you this to try? You should try this at home. This is a mail order company. It operates 5 regional distribution centers. It takes goods from regional warehouses to customers. Yours is to formulate the output-oriented multiplier model, the multiplier fractional problem, fractional programming problem. And then the same output-oriented, this time, do the linear programming problem for the multiplier, and then convert the multiplier to the envelopment model. Now you can see that here, the difference is that you have 2 inputs, labor and capital, and then you have 2 outputs. The delivery distance is the output, the distance the mail has to travel. And then the packages in thousands that are delivered. Okay, that are delivered at a time, that is it. You got to do this linear program for the center one. Center one here is the DMU1. Okay, so how do you do the formulation for DMU1? If I should say that you should do this, can you do it? Okay, you do the formulation for this DMU. Well, is a weighted output over the weighted input. Okay, is a weighted output. And because it's an output oriented, I'm not going to go deep into it. I'm going to give you another one where we are going to do together this time. So I've done it all here. You can look at it and then you can see the connection between this and both the envelopment and the multiplier model of all of that. Okay, you can look at it. I am more interested in taking you through this simple hypothetical example. This hypothetical data set is something I told you to write and come here. You're going to work a lot on this. Okay, you're going to write a lot on this, so please take note.